Second morning session with talk by Juan Maldacena from Institute of Advanced Study at Princeton, and his title is already there: Super Young Mills Scattering Amplitudes at Strong Coupling.
Well, thank you. Thanks to the organizers for organizing this wonderful conference at this wonderful city, and also thank you for the opportunity to speak at this conference. So I'll be talking about work that we've been doing with Luis Alday, who is sitting over there, and it's in a paper we already published, and some new things are in a paper that's about that will appear soon. So the goal of this work is to compute planar color-ordered Gluon scattering amplitudes at strong coupling using using strings in ADS 5 cross S5. So I remind you that color-ordered amplitudes are defined in the following way. So you consider planar diagrams, and you separate the diagrams according to the ordering of the gluons. So you pull out this piece that depends on the gauge indices of the gluons, and then there will be a piece which will be just a function of the gluon momenta and also the polarizations. So even though the total amplitude is completely symmetric under exchanges, this amplitude is only symmetric under cyclic permutations. Okay. Now, if often you would say that if we have this goal, so exactly what we're going to compute is this, and now trying to compute this looks like trying to go to battle against windmills, because these are objects which are not well defined in the gauge theory, and it's not a good idea to go to battle against windmills. And so what are we doing here? Well, yes, it's true, they are infrared diversion, but we can always introduce an infrared regulator, and people who do actual calculations use this as building blocks for infrared finite observables. So you sum these infrared divergent amplitudes for different number of gluons that contribute to a given physical observable, and the infrared divergence is cancelled, and in the end you get good finite results for well-defined physical observables. Now, in addition, another motivation for this work is that there is a very interesting conjecture for the all-order forms for these amplitudes in the MHB case. And this is a conjecture that was made by these people based on previous work, which says that the amplitude is the tree-level amplitude times function of the kinematic invariance and the infrared regulator. So this is a conjecture for the infrared regularized amplitude, and the whole dependencies with some overall functions here. I will give a more precise version later, but the point is that, for example, the kinematic dependence is completely fixed by their conjecture up to an overall function. So one would like to see whether one can take these amplitudes and compute them at strong coupling and see whether it agrees with this form, for example. So the final answer, so I'm just going to give you the final answer, and then I'll explain to you how we got to this final answer, is that the scattering process is described by a classical string wall sheet, a classical solution of the sigma model, of the ADS 5 sigma model. And the amplitude is given just by the action of the wall sheet, so it's exponential of the usual area formula. And all the dependence on the coupling is through the overall factor that involves the radius of ADS. So it's a function that goes like square root of lambda times some function which will depend on the kinematic invariance and also u, and also mu, which is the infrared regulator. Now we'll introduce two infrared regulators. So the first one we'll be introducing a brane in the infrared, and we'll use it to motivate the prescription we will use to define these amplitudes. And the second regulator will be dimensional regularization, which is the one we will use for doing computations and also to compare to the gauge theory results. So let's discuss the first regulator. So here we imagine putting d brane in the bulk, and this could arise, for example, if we take the gauge theory and we go to the Coulomb branch where we separate the various branes, or we give expectation values to the scalar fields. And then we can have open strings that the gluons will be open strings that live on these branes here at the bottom, here at this position, and then we scatter them with fixed gauge theory energy, and then that implies that the proper energy will be very large. So we want to keep the energy measured with relative to the gauge theory coordinates x fixed, and that implies that the proper energy that an observer sitting here sees is very large, given by this usual formula. So it becomes very large when C infrared is taken to infinity. So the boundary is at C equal to 0, and the infrared region is at C equal to infinity. So that implies that we'll have high energy scattering in the bulk, and high energy scattering is described by a classical string solution. So we are doing the high energy fixed angle scattering, so we keep the angles fixed and we scale up the energies, and in that regime we learn from work by Gross and Mende that the scattering, at least in flat space, is described by a classical string solution, and we expect that the same should be true in ADS space. Now, Polchinski and Strassler also considered high energy scattering in the gauge theory, but they considered the scattering of closed strings, and in their case they could do away without considering the full classical string solution, just with supergravity, but in our case we'll have to actually compute the classical string solution. Now it's convenient to describe the solution to do a t-duality on some of the coordinates. Now you might object that, well, you are doing a t-duality in some coordinates which were non-compact, and we'll do t-duality in time, which is also objectionable. But we are doing this just at the level of the classical equations. We are interested just in the classical solutions. So we can certainly do that. I mean, it's perfectly okay to do it at the level of the classical equations. It's just simply doing a transformation, describing the solution in a different way. And then once you found the solution, you could go back to the original coordinates. So there is no objection for doing t-duality. So we're going to t-dualize all the spatial coordinates, including time. We are in Lorentzian time, so we will also t-dualize the time coordinates. So we go from x to the coordinate y. Via duality on the wall sheet, and we'll also redefine the coordinate c. This is just an ordinary coordinate transformation, and after you do that, you get that the t-dual space also has the form of ADS5, and this will simplify the calculations because we'll have the isometries of ADS5 at our disposal to find the solutions. And also, what initially was momentum in all these spatial coordinates becomes winding in the y direction. So a string or an object that carries some fixed momentum along the x direction will become a string that is wound or stretched along the y direction by an amount which is proportional to its momentum. So in some sense, these y coordinates are like momentum space. And well, it's known that t-duality is some kind of Fourier transform. And so we are essentially, this t-dual ADS is like the momentum, some kind of momentum space ADS space. Now notice that when we do the t-duality, we also introduce a dilaton, and the dilaton will not be invariant under the conform. It will be a dilaton that is a function of C or a function of R, only R, so it will not be invariant under the conformal symmetries, but that will not matter at the level of classical solutions. So the classical solutions or the classical equations are invariant under full conformal symmetry. And in fact, this type of transformation was considered in the past, and it leads to some simplifications in the Green-Schwarz action, and was considered by Kalosh and Lightlike. So, yeah. So you want the question, was why is t-duality? Why is this the formula for t-duality? So what you want is to exchange the equation. So the equation of motion for x is d star dx over c squared equal to 0, and you want to exchange the equation of motion with the Bianchi identity. So this is the usual formula for t-duality. Right. Okay, so the final prescription is that we have the gluon momenta defines some winding in the y direction, and we have a sequence of now this winding is Lightlike because the momenta that we started with are Lightlike. So we have 2 points that are separated by a Lightlike distance, and then we have a sequence of momenta. We'll end up with a sequence of Lightlike vectors. So we have the first momentum is a Lightlike vector, second momentum is a Lightlike vector in a different direction, and so on. And the sequence here of Lightlike vectors is given by the sequence of momenta in the color order amplitude. So this is a sequence of momenta that lives on the boundary, and what we have to do is find the worldsheet that ends on that sequence. So here we have removed the infrared regulator, so we have put the brain all the way to the boundary of the so-called T-dual ADS space. I remind you that when we did this transformation, C going to infinity corresponds to r equal to 0. So we are putting the boundary conditions at r equal to 0. So the computation you have to do in the end is formally very similar to the computation you would do if you were computing Wilson loop expectation value, where the Wilson loop is given by this sequence of momenta. But so it's only formally. So in details, especially once we introduce the regulator, it will be slightly different. So all of this is in the T-dual coordinates, and we have temporarily removed the infrared regulator. So all we have to do is find this classical worldsheet and compute its area. Now, notice a couple of features that the leading order answer will be given by the area of this worldsheet, and is independent of the detailed states of the gluons. So the gluons could be in any of its 16 polarization states, and the answer we'll get to leading order will be independent of that. So the dependence of those polarizations should appear at the next order. And also notice that since it's independent of the polarizations, it will be the same for MHB and non-MHB amplitudes. So this statement is true for the leading order answer, already at the subleading term. So by subleading I mean the next term in the 1 over square root of lambda expansion. So that term could depend on the polarizations of the gluons. Now we have some symmetries of this problem, and the symmetry, well, I already mentioned it, is the conformal symmetry of the momentum space or T-dual coordinates, and will be useful for us for finding the solution. So it's not the symmetry of the full theory, as the dilaton you generate by doing T-duality is not invariant. But it's rather interesting that this type of symmetry was also observed at weak coupling. So the amplitudes that contribute at weak coupling, when you write them in momentum space, also have this momentum space conformal symmetry, which is not the same as the conformal symmetry of position space acting, Fourier transform. It's a different symmetry. And it's not clear what exactly how one should think about this symmetry. What's the origin of this symmetry is presumably because we have integrability. Okay, so now I'll describe how one finds the worldsheet. So for the case for gluons, it's especially simple to find the worldsheet. So we start first with a configuration of 2 infinite Lightlike lines that are meeting at the point. This configuration was considered in the past by Kruczynski, and he found the solution in this case. So it's some worldsheet that goes in the interior of ADS. And in any case, this solution will describe the behavior of the full solution near each of these cusps between 2 Lightlike lines. And then we apply a general conformal transformation in these T-dual coordinates, which is not the same as a general conformal transformation in the original coordinates. And we get the solution for 4 Lightlike segments. So even though naively we started with 2 Lightlike segments, when you view this solution in global ADS, actually Kruczynski's solution has 4 cusps and has 4 Lightlike segments. And then you apply general conformal transformation, and you can get the solution for a general 4-gluon amplitude. So, and it will be expressed as some equation in ADS. So you have a 5-dimensional space and 3 equations which define a 2-dimensional worldsheet. So here I just wrote the equation for S equal to t. For S different from t is a very similar equation which has a few more parameters, 1 more parameter. Now, finding the n-gluon solution, in principle, could be done, but well, we haven't done it, and it would require some more work because you cannot just generate it using this symmetry. But presumably, by thinking about integrability better, you will the classical integrability of the ADS5 sigma model, you will be able to find it. Now, if you compute the area of the surface, you will find the area is divergent. And so in order to deal with it, we introduce the second infrared regulator, which is dimensional regularization. So when people do gauge theory computations, they usually use dimensional regularization and compute the amplitudes in 4 plus epsilon dimensions. So to be more precise, what they do is they consider 10-dimensional super Young-Mills dimensionally reduced to 4 plus epsilon dimensions. So the size of the multiplet, of the supermultiplet, is kept fixed with 8 fermionics plus 8 bosonic components, but what you change is the number of volume dimensions over which the theory is defined. So now that's very similar to what we do when we consider p-branes with various values of p. So we can consider a dp brane with p equal to 3 plus epsilon. So if epsilon is an integer, this is the usual sequence of dp branes. And now we can take the formula for a dp brane as a function of p, which is defined for integer values of p, and then analytically continue the formulas for general values of p, and then go to 4 plus epsilon dimensions. So when we do that, well, this is the general form of the metric, and then we have here some function which depends on the p-dimensional gauge coupling and this transverse coordinate, and here there is some numerical constant which in principle was defined only for integer values of p, but we analytically continue it to generic values of p. Of course, there is some kind of ambiguity when you do that, but we hope we did it in the simplest possible way. So here this constant depends on the volume of the sphere, and so we analytically continue the volume of the sphere in the way that is usually done when you do dimensional regularization and so on. Now, so going to a different dimension is one part of dimensional regularization. The second part is to introduce the scale by noticing that the p-dimensional gauge coupling is functional. Well, it has dimensions, so one introduces a scale. And here there are some precise functions of epsilon one chooses, and we choose the same function of epsilon as people choose in the gauge theory computation. So here we choose exactly the same prescription that is chosen for the gauge theory calculation. And then when we do that, we find some divergent terms, and then some finite terms. And the finite terms have this form, and then some constant that one can compute also. Okay, so let's talk a little bit more about these divergent terms. So the structure of infrared divergences in gluon amplitudes has a very long story and is very well studied. The literature is much longer than the names here. And in the case of planar diagrams and conformal theory, well, in the case of planar diagrams, we get an infrared divergence per pizza slice here. I mean, the infrared divergences are coming from soft, low energy gluons that are being exchanged between these lines. And at the level of planar diagrams, the gluons from this region don't talk to the gluons from this region. So we'll, at least when we are interested in the infrared diversion part, and so we'll get one infrared divergence per pizza slice here. And so we have n gluons, we have n factors. Each of these factors, so these are the n factors, each of these factors will depend on the total momentum transfer that it goes through here, and of course also on the infrared regulator. And so they have a form which has poles 1 over epsilon square in dimensional regularization, and poles that go like 1 over epsilon. And a 1 over epsilon pole in dimensional regularization translates into a log square of the infrared regulator scale. So when you expand this in parts of epsilon, you'll get a log square of mu. Now, so these infrared divergences are characterized by two functions of lambda. So the first characterizes the leading infrared divergences, which go like log square, and then we have a function characterizing the subleading infrared divergences. Now, the first function is called the cusp anomalous dimension, and it's a function which also appears when you compute the anomalous dimensions or of high twist operators. So you consider operators with spin and compute their dimensions, and then if you expand the dimensions for large spin, you find that the term proportional to log of s is given by precisely the same function that appears there. And one can, well, it's well understood why the same function appears in both calculations. Now it's important that even though we call this a diversion, it doesn't make the amplitude infinite. It actually makes the amplitude 0, because these diversions is exponentiate, and they appear with such a sign in the exponent so as to suppress the amplitude. And physically what they are saying is that it is very improbable not to emit other gluons. So if we compute, let's say, an amplitude with given number of gluons, it's always going to be possible to emit some other low energy gluon, and so that's the physical origin of the diversions. Now, why do the divergences have this precise form? There is a very simple argument. So you replace the gluons by, so there are the gluons that have high energy or fixed energy, and then there are the low energy gluons, which have energy much smaller, that are exchanged between these two other gluons, and they have an energy much lower than the energy of these gluons here. So we can replace these high energy gluons by Wilson lines, then once you do that, once you replace the high energy gluons by Wilson lines, the configuration is invariant under two non-compact symmetries. One is to do boosts. So these are two gluons. Let's say you can imagine them colliding head-on onto each other. And you can imagine this cusp with Wilson lines extending in the x plus and let's say x minus directions. So the Wilson line configuration is invariant under boosts of that plane, and then also invariant under scale transformations. So when you compute the Wilson loop, the amplitude will be proportional to the Wilson, at least the infrared diversion part will involve the Wilson loop expectation value, which, since it's invariant under two symmetries, will have sort of the effective, so will have, the problem is similar to how you compute the free energy of a system that is invariant under translations in space and in time, which will have, you will have the total range along which you can do boosts and scale transformations times some local function of lambda. And so this, you cannot do boosts arbitrarily, because if you do too much boosts that reduce one of the momenta, for example this one, at some point the approximation that the momentum is large will fail, and so that will cut off the momentums in the UV direction by the momentum transfer, and similarly in the infrared direction they are cut off by mu. So in this way you get the log mu square over s, and you get that form of the infrared divergences. And so each of these two symmetries gives one factor of log, and that's why you get the log squared. Now the second function, g of lambda, characterizes the subleading infrared divergences. It was computed to 3 loops at weak coupling by these people, and I understand that there are groups computing it now at 4 loops. And it also, at least to the order it was computed, obeys the so-called maximal transcendentality principle, which we'll probably hear more about in other talks, that the function f of lambda also obeys. And we can compute it at strong coupling, and we find this answer. So we compute it at strong coupling by using the solution we described before. So now let me describe in more detail that Byrne, Dixon, and Smirnov ansatz. For the particular case of 4 gluons, they say that the amplitude is the divergent piece, which is of the form we discussed before, plus f of lambda times log s over t squared, which is exactly what we obtained using the Walsh calculation. And it agrees with their form once we use the strong coupling form for f of lambda. So this was the cusp anomalous dimension, which was computed at strong lambda first by Gabser, Klebanov, and Polyakov, and in this form of the Wilson loop by Kruczynski. And then, of course, now we have an exact integral equation which determines f of lambda for all lambda. That was derived in a paper by Weiser, Eden, and Staudacher last year. So we have this nice agreement, but we should remark that the 4-gluon amplitude is really completely determined by momentum space conformal invariance, and also the form of the infrared divergences. So this factor here is introduced so that the full answer will be invariant under conformal invariance of momentum space. Now for n gluons, Bernd, Dixon, and Smirnov propose an explicit but more complicated function of the kinematic invariance instead of this one, which in this case is not determined by momentum space conformal symmetry. So it would be nice to also check that case. So conclusions is that we gave a precise prescription for computing scattering amplitudes in ADS, and we checked their ansatz for gluons, and we observed the presence of this momentum space conformal symmetry, which also seems to be present at weak coupling, and whose role probably should be understood better. And we computed this function at strong coupling. And we can also consider similar processes involving local operators going to n gluons, sometimes called also form factor. So in the future, one would like to compute the solutions for n gluons and check the ansatz for n gluons. And one can ask whether the function g of lambda can be computed for all values of the coupling using integrability, so obtaining a formula similar to what Weissertin and Staudacher obtained. Now, also one would like to find solutions, explicit solutions for those form factors. And one would also like to understand the crossover from weak to strong coupling in shed physics. Well, thank you very much.
Any questions?
To what extent is there an exact relationship between the Yang-Mills gauge theory in 4 plus or minus epsilon dimensions and the string theory on ADS in 10 minus epsilon or whatever?
Yeah, that's a good question. I mean, one can ask whether, in some sense, it can be extended even at finite 10 and so on. I would probably expect that perhaps to all values in lambda, at least for the planar theory, there is a relationship.
But
at
large n,
proven. Is
it at large n there's an exact relationship?
Well, here we were only at large lambda, but I would expect that this relationship exists for all values of lambda in the planar theory, so for n equal to infinity in the top limit. Perhaps, but nobody has proven this. But it would be nice if it exists even for finite n.
Any other questions?
Well, could you just say another word about the very beginning? You have the gluon scattering effectively at high energy fixed momentum. High energy fixed angles.
Yeah.
So you're going to somehow borrow the Gross-Mende type of story?
Yeah.
How do you get from there to a string world sheet with the topology of a disk ending on those segments? Can you just go over that?
Right. So in order to explain that, I don't need to do any of this ADS story. All we have to discuss is just the scattering in flat space. So if we do Gross-Mende scattering in flat space for open strings, then we have the world sheet of a topology of a disk, because we are doing a disk amplitude. Now, ordinarily, the boundary conditions are put in the original coordinates. So we are saying that near the insertion of some vertex operators, the string has a certain momentum. So in general, can this be switched on? So in general, we have near those vertex operators, we have some boundary conditions which say that the world sheet goes like log of tau. Oh, it's not very clear. And when we do the t-duality, if we do the t-duality, we will find that this goes like k mu log of sigma, where the world sheet, so near one of these insertion points, we have tau and sigma. So you see that in the t-dual space, the world sheet winds sort of around the sigma direction. So if we do this t-duality, which we can also do it in flat space we would have a configuration of Lightlike segments in Lorentzian, in the t-dual Lorentzian space, and then we would have an actual physical world sheet ending on this space. Notice that also the Gross-Mende solution is pure imaginary. After we do the t-duality, we get a real solution, so it's a real world sheet that ends on that Lightlike contour.
In the polygon you drew,
Yeah.
the segments in the polygon can correspond to those black lines or to the gaps at the top and bottom?
The segment corresponds to the top and the bottom.
Okay, thanks.
Yeah.
Any other questions? Okay, if there are no other questions, let's thank the speaker again.